Welcome to This Explainer. Okay, so today we're tackling something pretty crucial, bridging a very specific engineering readiness gap. We're going to move way beyond just looking at power flow equations and nodding along. We're talking about actually formulating, troubleshooting, and defending a Newton-Raphson power flow solve. Whether you're gearing up for an exam, a high-stakes interview, or a big project meeting, this Moonbow Readiness Kit orientation, it's designed to give you the exact framework you need to absolutely nail it. Let's get right into it.
Here's our quick roadmap for this orientation. We'll hit the readiness gap, define the power mismatch, look at bus roles and states, walk through the Newton correction loop, talk about failures versus engineering acceptance, and wrap up with how to actually use the readiness kit workflow.
All right, Section 1, the readiness gap. So, ask yourself this. Is recognizing the equations the same as building and defending the solve? Well, no, not at all. Look, memorizing a Jacobian matrix just isn't going to cut it. That gap between merely memorizing things and actually applying them, yeah, that shows up incredibly fast the second someone changes the bus types on you, or asks what exactly goes into the mismatch, or hands you a converged case that has a completely implausible voltage. True readiness means you can actually explain what the method is doing, construct the right reduced problem from scratch, and, this is key, recognize when an answer shouldn't be trusted, even if the math says it converged.
Moving on, Section 2, defining the power mismatch.
Before we even glance at the algorithm itself, we've got to get really clear on what the power flow is physically trying to solve at steady state. Every single enforced bus balance has to be satisfied. See, the network relation connects current and voltage through the Y-bus matrix. And because complex power non-linearly depends on voltage magnitude and angle across the entire network, well, it's kind of like trying to balance a giant web of springs. You adjust one node, and bam, it shifts the forces everywhere else. That non-linearity is exactly why we have to use an iterative approach like Newton-Raphson in the first place.
So that brings us to the power mismatch. Imagine this. A trial voltage state produces your calculated real and reactive power injections. You take those calculations, compare them with the specified injections of your system, and you get a residual. That right there is the power mismatch. Now listen closely, because you have to strictly stick to this convention. Mismatch equals specified minus calculated. Don't flip it. If you flip this convention, your entire correction step is going to move in the completely wrong direction. Newton-Raphson uses the local sensitivity of those calculated injections to pick a state correction that is intended to strictly reduce that residual mismatch down to zero.
Okay, Section 3, bus roles and states. Let's look at how our formulation is reduced before we even differentiate it. What actually stays in the reduced state? Well, that's entirely dictated by the bus roles. For a slack bus, voltage magnitude and angle are known, while real and reactive power just emerge. At a PQ bus, real and reactive power are known, so that makes both voltage angle and magnitude are unknown states. But let's zoom in on the PV bus for a second. Here, real power and voltage magnitude are specified, making the angle our state, while reactive power emerges. But wait, there is a massive constraint you've got to remember here. A PV bus can only maintain its voltage set point while its controlling device stays within its reactive power rating. If it hits that Q limit, it literally cannot hold that voltage anymore. So, your final reduced state contains every non-slack angle and the voltage magnitudes of your PQ buses.
Which brings us to Section 4, the Newton correction loop.
Let's see how all of this builds into a really tightly controlled sequential loop. Step 1. At your current state, you calculate the power injections. Step 2. Form the mismatch. And remember, strictly specified minus calculated. Step 3. Build that reduced Jacobian with its 4 sensitivity blocks, which are real and reactive power with respect to angle and magnitude. Step 4. Solve this linear system to get your state correction. And finally, Step 5. Update the state and test the residual again. Guys, the sign of your update is not just some random guess. It strictly follows from how you defined the residual and the Jacobian. State your convention and preserve it through every single row and column. Absolutely crucial.
Section 5, failures and engineering acceptance.
In the real world, solves behave badly. They just do. And when things go wrong, you have to find the failure layer before you just start making arbitrary changes to the algorithm. If your dimensions disagree, it's usually pointing to bad bus treatment or a flaw in how you reduce the state. If your very first correction absolutely explodes, check your radians, check your signs, or look at your derivatives. And remember what we just said about the PV bus? If it hits its reactive power limit, it fails to hold its old voltage set point, and you actually have to physically change its treatment in the solve. You've got to convert it to a PQ bus. And what if your residual just stalls out?
Well, a small residual doesn't magically fix bad data. Check your model, check your initialization. Basically, ask yourself, what nonlinear problem did I actually just ask Newton to solve? This leads us to a fundamental distinction in power engineering. We absolutely have to differentiate between numerical convergence and engineering acceptance. Numerical convergence, that just answers a super narrow question. Are the enforced residuals small relative to your chosen tolerance? That is literally it. Engineering acceptance, on the other hand, asks way more. Are the reactive controls actually consistent? Are limits respected? Are the resulting voltage magnitudes and angles physically plausible? Do the directional branch flows and total losses actually reconcile with reality? You see, a perfectly mathematically converged result can still be completely unacceptable in the real world, and a technically strong engineer can explain exactly why.
Finally, Section 6, the Readiness Kit workflow. To build out your verified transfer skills, you're going to follow a very specific loop. You'll start by establishing a baseline. Then you'll tackle the original problem challenge. And hey, if you get stuck, you don't just go look up the answer. Instead, you'll use the coach cards Derive, Debug, or Defend. These are specifically designed to help identify your unique gaps, force you to provide your own explanation of the concepts, and then test your transfer of that knowledge on a completely different, verified problem. The goal isn't just to mindlessly flip through pages in a workbook. No way. The goal is to walk away with hard evidence that you can perform and troubleshoot under dynamic, changing conditions.
So choose the real-world situation you're prepping for right now. Maybe it's an exam, an interview, a big meeting, or just a professional refresher. Record your baseline confidence rating right now. Then, take the diagnostic without using your notes and absolutely without using any AI. Your very first honest attempt is the starting data for the entire kit. So here's my final question to you. When the parameters change and the solver fails, are you just going to be guessing at matrices, or are you ready to actually defend the solve? Trust the process, go record your baseline, and let's get to work.